so welcome again. And in the last discussion, we were discussing about the similarity solution of the energy equation. So that was the exact solution. Now you might have guessed already that our next step will be what? Will be to go for the integral method. That is we have derived the momentum integral equation, and likewise we will now derive the energy integral equation. Okay, so let me do that. So already you know the first step, that is to write the energy equation. Okay, let me zoom it. So this will be the energy integral equation. Okay, so what will be the first step to write the energy equation? So energy equation for the boundary layer on a semi-infinite flat plate. So that will be what? U delta t delta x plus v delta t delta y is equal to alpha delta t always delta y square, because x is large than y. The scale of x is larger than y. Now okay, so for simplicity I can do it like this. So I can write this term as, this should be a very easy step for you, this minus t of just applying the product rule, and this term as what? Similarly t v y minus t del v del y, right? Okay, so and now if I add this one and this one, then what I will get? I will get del tu by del x plus del tv plus del y minus t into divergence of v, del u del x plus del v del y. And for an incompressible flow, 2D incompressible flow, this is 0, right? For a 2D incompressible flow. So this is the conservative form and this is the non-conservative form, this one. Okay, in CFD, conservative form has its own benefits, and in also the non-conservative forms are important in some areas. So we will here talk about the conservative forms. Okay, I mean this momentum integral equation. Also you can do the same by the non-conservative form. Ultimately, after all the mathematical manipulations, both will arrive at the same result. So your homework will be do the same exercise on this. Okay, so now let me write the energy equation in this form again. So this is equal to alpha delta t delta y square. So what will be the next step? To integrate, right? dy 0 to delta t 0 to delta t dy is equal to alpha. So I am writing it directly now, 0 to delta t. Okay, so now okay, so here if I apply the Leibniz rule, okay, so what was the Leibniz rule? So I also always tend to forget the Leibniz rule, so I always write it beforehand because I also get confused. So you always remember the Reynolds transport theorem. Okay, so this will be del x of tu dy 0 to delta t, that will be equal to del tu del x 0 to delta t. Okay, so plus the outgoing flux, that will be d delta t dx into tu at uh, delta t comma y delta t comma x, right, and minus d of 0 this tu 0 comma x. So if you substitute this x by t, then it almost becomes the Reynolds transport theorem. So this is the global change, this is the change in control volume, and this is the outgoing flux, and this is the incoming flux. So this way you can remember the Leibniz rule. Okay, so if I apply here, so this directly becomes 0. Okay, and what is this? So this is d delta t dx, right? It is d delta t dx and t into u at delta t. So t at delta t is t infinity, u at delta t is not u infinity. Okay, so what we will do here is tu at, okay, so we will write, so this will be something u at delta t. So we write this total term as t into u at delta t. Okay, so this term becomes here, this term is equal to what, del x of, and now here I can write ddx because I have already integrated with respect to y, so it will be only a function of x. This minus what, d delta t x tu at this, right? Okay, so and this will be ultimately ddx tu dy minus t infinity u at delta t x. Okay, so let us see, is u delta t is a function of x? Yes, it is a function of x, right? So what I can do here, but t infinity is not a function of x, right? And this delta t I can write as 0 to y, right, 0 to delta t dy. Okay, okay, so we have calculated this term, and this term will be what? So let us write del y of t into v dy 0 to delta t is equal to t into v 0 to delta t, right? So at 0 v is 0 because of no penetration, at infinity it will be what, t infinity into v at delta t. This also we cannot say if it is 0. Okay, okay, so now what do we have? We have required, so we have calculated this first term, sorry, We have calculated the first term, the second term, the third term. So let us write accordingly. We will have del x, I will write capital DD x of this into tu dy minus t infinity u delta t ddx of 0 to delta t. So this is delta t, right? Okay, this is delta t, this will be dy. Okay, then plus t infinity into v delta t is equal to minus alpha del t del y at y equal to 0. Why? Because at, so this term will be what? This term will be del t del y at y equal to delta t minus del t del y at y equal to 0, but we know that this is 0, right? Because at the edge of the temperature boundary layer, the delta t, I mean the slope of the temperature profile, that becomes 0. Okay, so now let us see what can we do here. Okay, so what do we have now? Here this u infinity, u at delta t and v at delta t are there, so this is not equal to u infinity. Okay, had it been delta instead of delta t, then we could have written that u delta at is equal to u infinity. Okay, so now how can you formulate? So this is what? This is u infinity and at a particular, I mean u delta t at a particular x. So this will be for sure a function of x. So this u cannot take inside this, it seems like that. Okay, so now let us write the continuity equation again. So in continuity we will have del u del x plus del v del y is equal to 0, again integrating with respect to y. So del u del x dy 0 to delta t plus, I am again writing it directly, 0 to delta t is equal to 0. So here I will have ddx of 0 to delta t u of dy. Okay, minus what? So minus d of delta t dx, okay, into u at delta t comma x. So this will be equal to v of delta t, because v of 0 is equal to 0. So I have written this step from the Leibniz rule. I have already worked with the Leibniz rule for several times until now, because I have applied it in the momentum integral equation. That is why I am not elaborating each step again. Okay, I am taking the advantage of that. So now then v of delta t is equal to what? Dx into u infinity. I mean, again I am telling it as u infinity, but that is incorrect. I apologize for that. So this becomes this, right? So now I can put this v infinity here, right? I can put the v, I have already derived the v infinity. Now I can put the expression here. So let me copy this equation. Okay, copy, and I will paste here. Okay, so I have this and this expression of v infinity. So if I put that v infinity, so let me write this expression again, ddx du dy, right? Then what do I have? Then I have t into u delta t, then d delta t del x plus t infinity into, instead of v delta t I can write d delta t dx into u infinity again, oh god, minus ddx of what, this delta u dy, right? Okay, so let me just check the calculations once more. I think I have done something wrong. Have I done something wrong? No, it is correct. Okay, so this will be equal to minus alpha del t del y at y equal to 0, correct? Okay, so now if I simplify further, then see that this term and this term is being cancelled out, right? So fortunately, by finding out v delta t, we have got rid from this term also. Okay, so this will be du dy delta t minus t infinity ddx 0 to delta t u dy. So that is equal to minus alpha this thing, right? Okay, so first of all, t infinity we are not uh, taking as a function of x. Here t infinity is not taking a function of x, and that is why we can write this as, okay, so let me write it uh, from the scratch. So this I can write as what? I can put the t infinity inside the bracket, and then there will be a minus this term, this whole term into dt infinity dx. So this term should have been there, but as I am considering that t infinity is not a function of x, then this is 0. So then this becomes ddx of, right, t into u dy minus, okay, ddx of u dy. Okay, now I can, t infinity is not a function of, neither is it a function of x nor is it a function of y. So I can take the t infinity inside the integral here, and I can write this, that is equal to minus alpha del t del y at y equal to 0. So this is ultimately I am getting u common t minus t infinity dy, okay, ddx of this equal to minus this. So you see that we have got a similar expression that we derived for the momentum integral equation. Okay, so this is the energy integral equation. Now the next step is the same, that we will assume some temperature profile. Now I have already told you in detail that what should be the criteria uh, based on which you should take your assumption of these profiles. I have talked about that in detail. So if you have forgotten already, you should revise that, okay? Because the same thing will apply here. So there is no meaning in wasting time by again asserting the same. So I am taking here a cubic profile again. I took this cubic profile for the velocity also. So here the boundary conditions at y equal to 0 you have the temperature equal to T wall, then at y equal to delta T we have T equal to T infinity, then at y equal to delta T you also have uh, del T del T y equal to 0, then at y equal to 0 what if you see the actual energy equation, this one. Okay, so at y equal to 0 you have u equal to 0 for no slip, b equal to 0 for no penetration, that means this is equal to 0. Okay, so I have seen that many of the students think that this is some boundary condition that we assume, but that is not the case. This has to come from the problem. Okay, otherwise you cannot take this. So now what you can do is that you can define some non-dimensionalized temperature profile, that is T minus T infinity by this minus this. Why I am taking a profile that is in this form? To simplify the problem. So non-dimensionalization is done basically for two reasons. I mean, the objective should be in the mind, that why I am doing the non-dimensionalization. So first and foremost uh, reason is to simplify the algebra, to simplify the problem. Now you can non-dimensionalize a single variable by many things. Like if you have let us say that if you have a pipe, okay, then you have two predominant length scales as for the pipe, L and the diameter D. Now if you have the coordinate system x and y, you can define a non-dimensionalized variable x bar like x by L. You can also define it by x by D. Now both are correct in terms of mathematics, both are correct. Okay, so but you should choose the one, okay, that will simplify your problem more. Also you should choose the one that will govern the physics. Okay, like in the boundary layer we know that for the x, the for the x we should the non-dimensionalization variable as L. Okay, so we have defined this. Now inside the boundary layer, if you take it as L, the y you take it as L, there will not be any mistake in terms of mathematics, but the physics will not be uh, uh, I mean the physics will not be depicted by that non-dimensionalization. So non-dimensionalization should be such, it should obey the physics. In that case the non-dimensionalized equation itself will tell you about the physics. And if you are not taking the variables with which you are non-dimensionalization, the variables with which you are non-dimensionalizing, then if those variables are not as part with the physics, then you will not get the associated physics with the problem from the non-dimensionalized equation. So we will see further that in many advanced problems in heat transfer and as well as fluid mechanics, first what we do is, okay, so let us say that we have the continuity equation. Okay, so here in many cases we know the UC, we know the XC, we know the YC, but we don't know the VC. Okay, so what we do is we find this VC from the scaling analysis, and then we use that VC to non-dimensionalize the V. You understand what I am telling, that uh, this Vc is not known a priori. So you can take V by U infinity as your non-dimensionalized V, but you know that this U infinity is not the actual scale of V, that is the V is not the order of U infinity. So what you should do is, from the physical equations you should find a relevant scale of V, that is here the Vc, then you non-dimensionalize V with the Vc that you have find from the physical equations. Okay. So from that point of view, I have derived this theta, that is t minus t infinity, by t wall minus t infinity. So why I have defined it like that? So just you put the boundary conditions for this theta. So see, at y equal to 0, t equal to t infinity. So then this becomes at, so again I am defining another variable for the y coordinate, and that is eta, eta equal to y by delta t. Okay. So this boundary condition becomes at eta equal to 0, theta equal to 1. This becomes at eta equal to 1, theta equal to 0. This becomes at eta equal to 1, d theta d eta equal to 0. This becomes at eta equal to 0, d2 theta d eta 2 equal to 0. You see that all the boundary conditions are having some numerical numbers, and those numbers are also between 0 and 1. So this problem has boiled down to a very simplified problem. Okay. And if you also put this theta in this equation, in this assumed profile, then you will get what? Okay. So uh, so then t minus t infinity. Okay. So you will get theta as a function of eta. Okay. Okay. So actually this profile should be, uh, what you should do is, you assume some, you assume your profile like theta is equal to some a plus beta plus c eta q plus d eta to the c eta square plus d eta q. Then you find a b c d from these boundary conditions. Okay. Then the algebra will be less. Otherwise, if you use this formulation, then in the constant a b c d we will have this t wall and t infinity. Okay. That will uh, that will add more complexity in your algebra. Okay. Now for delta less than delta t. Okay. So what, now you have to put this t into, or the theta. Now you can see that if you want to bring theta here, then you just divide this and multiply this, as both t wall and t infinity are constant with respect to y. Okay. So then you are getting u into theta. Okay. So for, okay, I am writing here only because I want you to see this equation. So for, now you have another variable here u. So for Prandtl number much less than 1, what do we have? Prandtl number is nu by alpha, and that is the measure of the delta by delta t. So delta by delta t is much less than 1, that means delta is less than delta t. So delta is inside delta t, then I have told you already, then you can take u to be almost u infinity at all the regions. Okay. But so then this u becomes u infinity and you solve your problem. But if your Prandtl number is much greater than 1, then your delta is much greater than delta t. Then you cannot take u as u infinity, then you have already derived the solution for u. So you can take this the actual solution. Okay. Or you can take the integral solution. You can take anything, obviously this will give you more accurate result. Okay. So if we consider that delta is greater than delta t. Okay. So now these are some mathematical exercise only. So that mathematical exercise gives us nu x is equal to 0.331 Prandtl number to the power 1/3 and Reynolds number to the power half, and this is for Prandtl number much greater than 1. So this is the integral solution. Okay, integral. And if you want to find the actual solution, and then what was that? Okay, the actual solution was what? I have forgot that. So this is 0.332, right? Yes, this one. So you see that we got here 0.331. So very accurate solution. So we have got a very accurate solution, 0.332, but we have avoided the complexities of the similarity solution. Okay, so this is the exact. So this was the power of the momentum integral method. Okay, so now what I will do is I will share you my upcoming plan on this discussion series. That is, I have covered the basics of the external force convection. Okay, so these are the basics. Okay, so there are some advanced topics like arbitrary wall temperature. That is, if this is your flat plate, maybe you start heat from here, maybe you start heat from, so, and this can be also the case from here to here you have T1, then you have T2, then you have T3. So there is a step change in the temperature. So for all this case there are some solutions. Also you have the flow over wedges, also you have the suction flow and the uh, suction and blowing. Okay, so for all these cases we have some solutions. So up till now whatever I have taught on external force convection, those were the basics. I will cover the advanced topics again, I mean after it, but for the time being now I will switch the discussion into the internal force convection. Okay, I will start with the internal force convection for the pipe flows. Okay, then I will go for the parallel plates, then I will again come to the advanced topic of the external force convection, then I will try to cover some interesting topics on the internal force convection. Those are the advanced topics for the internal force convection, then we will go to the natural convection. So this will be the roadmap for our upcoming discussions. So until that, thank you, and if you have got any questions, post it in the comment box. I will try to answer it. So, and if you have any suggestions also, you should post it. So thank you, goodbye, and take care.